Hey everyone. In the first week of lecture, I told you that all of our basic data types, like strings and ints and booleans, could be encoded in the lambda calculus. That is, encoded in a system where the only primitive type is really a function. This might seem a little strange to you. After all, how can a number be a function? But if you keep in mind that the fundamental idea is not capturing the Platonic essence of a number, but instead just representing the number, well, then it starts to seem a little more believable. So in this video, I'm going to show you the most famous encoding of both Booleans and the natural numbers in the lambda calculus. And by the way, this encoding is called the Church encoding because it was invented by Alonzo Church. And I guess I should warn you that rather than use the syntax of the lambda calculus directly, I'm going to write this in bracket instead. But keep in mind that everything I write today can be translated directly into the lambda calculus. So let's get started with Booleans. I'm going to define true in the following way. It's going to be a function, because remember in the lambda calculus everything is a function, and it's going to take two arguments a and b, and then it's going to return a. And similarly, false is going to be a function that takes two arguments a and b and returns b. And you might wonder, why in the world did I pick these two representations of true and false? And the answer is actually pretty simple. By defining true and false in this way, we get if statements for free. So for example, if I wanted to say if the Boolean, then the consequence, else the alternative, then this can be implemented directly just by applying the Boolean to consequent and alternative. So this gets translated directly into bool, consequent, and alternate. If the Boolean is true, then we return the first argument. And if the Boolean is false, we return the second. Exactly the same behavior that we would want if we were writing an if statement. Now we're going to talk about representing the natural numbers. If we want to represent the number n in the lambda calculus, if we want to represent the number n using only functions, then one very natural way of doing this is by applying a given function n times. And let me explain what I mean by that with an example. So I'm going to define 1, which is going to be a function taking in two arguments, f and x. And all it's going to do is apply f to x. And where does the actual 1 come in? It's because I'm applying f to x once. If I wanted to define 2, then I would apply f twice. Similarly, if I wanted to define, 5, then I would apply f 5 times. And I could keep on going, of course, but let me just say, I also want 0, because 0 is very important. And 0 means that I've applied f 0 times, so in fact, I just return x. Now the last thing I'll tell you about, okay, so these are representations of the natural numbers. But of course, we don't just want to name the natural numbers. We want to be able to perform operations on the natural numbers. So a good question to ask would be, using this representation of 0, 1, 2, and 5, how am I going to add two numbers together? How am I going to say that 1 plus 1 equals 2? And to do this, we're going to define add, which takes in two numbers, and then hopefully outputs n plus m, and hopefully outputs the representation of n plus m. And now I want to return a new function that applies f to x n plus m times. So that is, I want to define a function that takes in f and x, and then applies f to x n plus m times. So let's do that. First, we're going to apply m to f and x, And remember what this does is it applies f to x m times. And now we have n times left to go, so we're just going to apply f to the results n times. And that's about it. As an exercise, you might want to try to figure out how you could implement subtraction, multiplication, and even exponentiation using this representation of natural numbers. And then for fun, if you'd like, you could even try to figure out how to extend this definition to the integers, and then to the rational numbers. And then, if you're feeling up to it, floating point approximations to the real numbers. Thanks for watching, and have a great day.